Have you ever wondered how your phone can rotate a photo perfectly, or how GPS systems calculate the shortest route between 2 points? The mathematics behind these everyday technologies relies on two fundamental concepts we'll explore today. Today, we're going to master two essential mathematical concepts: linear transformations and the equation of a straight line. These aren't just abstract mathematical ideas, they're the building blocks behind computer graphics, artificial intelligence, and countless real world applications. First, we'll explore linear transformations. These are special mathematical functions that take vectors as input and produce vectors as output, while preserving the fundamental structure of vector spaces. Think of them as rules that transform shapes and objects in predictable, consistent ways. Next, we'll dive into the equation of a straight line, y equals mx plus c. This simple yet powerful equation describes every straight line on a coordinate plane. The letter m represents the slope or gradient, while c represents the y-intercept, where the line crosses the y-axis. Throughout this comprehensive tutorial, you'll discover how these concepts power modern technology. Linear transformations drive computer graphics, image processing, and machine learning algorithms. Meanwhile, straight-line equations form the foundation of data analysis, economic modeling, and artificial intelligence predictions. By the end of this video series, you'll have a solid understanding of both linear transformations and straight-line equations. We'll work through detailed examples, explore practical applications, and give you the tools to solve real problems. Whether you're preparing for exams or building a foundation for advanced mathematics, this knowledge will serve you well. A linear transformation is one of the most fundamental concepts in linear algebra. Think of it as a special type of function that takes vectors as input and produces vectors as output, but it does so in a very specific way that preserves the linear structure of vector spaces. Formally, a linear transformation T is a function that maps vectors from one vector space V to another vector space W. The key word here is preserves. It means that the linear relationships between vectors are maintained after the transformation. For a function to be called a linear transformation, it must satisfy exactly two properties. These properties ensure that the transformation behaves linearly with respect to vector addition and scalar multiplication. The first property is additivity. This means that if you take two vectors u and v, add them together, and then apply the transformation t, you get the same result as if you applied t to each vector separately and then added the results. Let me show you this visually. Here we have two vectors, vector u in blue and vector v in green. When we add these vectors using the parallelogram rule, we get the red vector u plus v. The additivity property guarantees that no matter what linear transformation we apply, transforming the sum u plus v will always give us the same result as transforming u and v separately, then adding those results together. The second property is homogeneity, also called scalar multiplication preservation. This means that if you multiply a vector by a scalar c and then apply the transformation, you get the same result as applying the transformation first and then multiplying by the scalar. Here's a visual example. We start with vector u in blue. When we multiply it by the scalar 2, we get the orange vector that's twice as long in the same direction. The homogeneity property ensures that this scaling relationship is preserved under any linear transformation. This means that if we apply a linear transformation t to the scaled vector 2u, we get exactly the same result as if we transformed u first and then multiplied the result by 2. This property ensures that scaling relationships are preserved. One of the most powerful aspects of linear transformations is that they can always be represented by matrices. When we have a linear transformation T, we can find a matrix A such that applying the transformation to any vector x is equivalent to multiplying that vector by the matrix A. Here's a concrete example. If we have the matrix A with entries 2, 1 in the first row and 0, 3 in the second row, and we want to transform the vector with components 1 and 2, we multiply the matrix by the vector. We calculate 2 times 1 plus 1 times 2 equals 4 for the first component, and 0 times 1 plus 3 times 2 equals 6 for the second component. So our input vector 1, 2 is transformed to the output vector 4, 6. This matrix representation makes linear transformations incredibly useful in practice. We can easily compute transformations, compose them by multiplying matrices, and analyze their properties. The key insight is that these two simple properties, additivity and homogeneity, are powerful enough to completely characterize linear transformations and connect them to matrix algebra. Now that we understand what linear transformations are, we need to explore their key properties and different types. These properties help us classify and analyze transformations systematically. Linear transformations have 5 fundamental properties that define their behavior and help us understand how they work. First is linearity itself. This means the transformation preserves vector addition and scalar multiplication. If you add 2 vectors and then transform, you get the same result as transforming each vector separately and then adding. The kernel, also called the null space, contains all vectors that the transformation maps to the 0 vector. This tells us what information the transformation loses. The image or range contains all possible output vectors. The rank is the dimension of this image space, telling us how many dimensions the transformation preserves. Nullity is the dimension of the kernel. There's a fundamental relationship called the rank-nullity theorem. Rank plus nullity always equals the dimension of the input space. Linear transformations can be classified into 3 important types based on how they map vectors between spaces. An injective or one-to-one transformation means different inputs always produce different outputs. This happens when the kernel contains only the 0 vector. A surjective or onto transformation means every vector in the output space is the image of some input vector. The image equals the entire codomain. A bijective transformation is both injective and surjective. These special transformations have inverse transformations and preserve all information. Let's examine a transformation from r squared to r cubed that is injective but not surjective. Consider this transformation matrix A. It takes a 2D vector and embeds it into 3D space by adding a 0 as the third component. To check if this is injective, we find the kernel. We need to solve a times x equals 0. This gives us x equals 0 and y equals 0. Since the kernel contains only the 0 vector, this transformation is injective. To check if it's surjective, we find the image. The image is spanned by the column vectors, which form the xy plane in 3D space. Since the image is only a 2D plane within 3D space, this transformation is not surjective. It cannot reach vectors with non-zero z components. Now let's look at a transformation from r cubed to r squared that is surjective but not injective. This projection matrix takes a 3D vector and projects it onto the xy plane by simply dropping the z-coordinate. To check if this is surjective, we ask, can we reach any vector in r squared? For any 2D vector, we can choose a 3D vector with the same x and y coordinates and z equals 0. For injectivity, we find the kernel. We need x and y to be 0, but z can be anything. The kernel is the entire z-axis. Since the kernel contains non-zero vectors, this transformation is not injective. Many different 3D vectors map to the same 2D vector. Finally, let's examine a transformation that is both injective and surjective, a bijective transformation. Consider this rotation matrix that rotates every vector in the plane by 90 degrees counterclockwise. To check if this is injective, we can compute the determinant. Since the determinant is 1, which is non-zero, the kernel contains only the 0 vector. For surjectivity, rotation preserves all distances and angles, so every vector in the plane can be reached by rotating some other vector. Since this transformation is both injective and surjective, it's bijective. This means it has an inverse transformation, a 90-degree clockwise rotation. Bijective transformations are special because they preserve all information and can be completely reversed. They establish a perfect one-to-one correspondence between input and output spaces. Linear transformations aren't just abstract mathematical concepts. They're powerful tools used everywhere in our digital world. From the graphics on your phone to the algorithms that power artificial intelligence, linear transformations are working behind the scenes. Linear transformations have 4 major application areas that directly impact our daily lives. First, computer graphics use them for every visual effect you see on screens. Second, Data analysis relies heavily on linear transformations. Principal component analysis, or PCA, uses linear transformations to reduce complex datasets into simpler forms while preserving the most important information. Third, machine learning and artificial intelligence use linear transformations in neural networks for image processing, feature extraction, and pattern recognition. Every time you use face recognition or image filters, linear transformations are at work. Finally, linear transformations appear in simple everyday tasks. Converting temperatures, scaling recipes, calculating taxes. These are all linear transformations that follow the same mathematical principles. Now let's work through 3 specific examples to see how linear transformations work in practice. Our first example is image scaling, a fundamental operation in computer graphics. When you resize an image on your computer or phone, you're applying a scaling transformation. This transformation multiplies each coordinate by a scaling factor. Let's say we want to scale an image by a factor of 1.5 in both directions. Let's apply this transformation to a specific point. If we have a pixel at coordinates 2, 3, we multiply it by our scaling matrix to find its new position. Now we perform the matrix multiplication. We multiply the scaling matrix by the point coordinates. The first row gives us the new x-coordinate, 1.5 times 2 plus 0 times 3 equals 3. The second row gives us the new y-coordinate, 0 times 2 plus 1.5 times 3 equals 4.5. So our transformed point is at coordinates 3, 4.5. This means the pixel that was originally at position 2, 3 is now at position 3, 4.5. It has moved further from the origin, making the image larger. This same transformation is applied to every pixel in the image. Our second example shows how temperature conversion is actually a linear transformation. Converting from Celsius to Fahrenheit follows the formula F equals 1.8 times C plus 32. This is a linear transformation because it has the form y equals mx plus b, where m is 1.8 and b is 32. The multiplication by 1.8 scales the temperature, and adding 32 shifts it to account for the different 0 points. Let's convert 25 degrees Celsius to Fahrenheit. We substitute C equals 25 into our formula. F equals 1.8 times 25 plus 32. First, we calculate 1.8 times 25. This equals 45. This is the scaling part of our linear transformation. Finally, we add 32 to get our result. 45 plus 32 equals 77 degrees Fahrenheit. The addition of 32 is the translation part of our linear transformation. So 25 degrees Celsius equals 77 degrees Fahrenheit. This linear transformation preserves the proportional relationships between temperatures while adjusting for the different scales. Our final example explores how linear transformations are used in data analysis, specifically in principal component analysis, or PCA. This technique helps us understand complex data sets by finding the most important patterns. Imagine we have data about students with 2 measurements, hours studied and test scores. PCA uses linear transformations to find the direction that captures the most variation in our data. Here's our sample data. Each point represents 1 student. Notice how the points tend to follow a diagonal pattern. Students who study more hours generally get higher test scores. PCA finds the principal component, the direction that captures the most variation in the data. This becomes our new coordinate system. The linear transformation rotates our data to align with this principal direction. The PCA transformation matrix rotates our coordinate system. If the principal component makes a 45-degree angle with the x-axis, our rotation matrix uses cosine and sine of 45 degrees. When we apply this transformation to our data point at 1, 1.2, we get new coordinates in the principal component space. Let's calculate. The new x-coordinate is 0.707 times 1 minus 0.707 times 1.2, which equals negative 0.141. The new y-coordinate is 0.707 times 1 plus 0.707 times 1.2, which equals 1.555. So our transformed point is at approximately minus 0.141, in the new coordinate system. This transformation reveals the underlying structure in our data. The first coordinate tells us how much each student deviates from the main trend, while the second coordinate represents their position along the main trend line. This is how PCA reduces complex data into simpler, more meaningful components. Now we shift our focus to one of the most fundamental equations in mathematics, the equation of a straight line. This equation, y equals mx plus c, is the key to understanding how lines behave on a coordinate plane. In this equation, we have two crucial components. The letter m represents the gradient, also called the slope, which tells us how steep the line is. The letter c represents the y-intercept, which is where the line crosses the y-axis. To understand these concepts better, we need to visualize them on a coordinate plane. Here we have our x and y axes, which form the foundation for plotting any straight line. Let's start by understanding the gradient, or slope, represented by m. The gradient tells us the steepness and direction of our line. It can be positive, negative, or even zero, and each case creates a very different looking line. When m is positive, the line slopes upward from left to right. For example, if m equals 2, the line rises 2 units vertically for every 1 unit it moves horizontally to the right. When m is negative, the line slopes downward from left to right. Here's an example where m equals -1. Notice how the line falls 1 unit vertically for every 1 unit it moves horizontally to the right. When m equals 0, we get a horizontal line. The line doesn't rise or fall at all, it stays perfectly flat. In this case, our equation simplifies to just y equals c. Now let's focus on the y-intercept, represented by c. This is the point where our line crosses the y-axis, which happens when x equals 0. The y-intercept tells us the value of y at this crossing point. Let me demonstrate this with a clear example. Here's a line with the equation y equals x plus 3. The y-intercept is 3, which means the line crosses the y-axis at the point where y equals 3. Notice that when x equals 0, we substitute this into our equation, y equals 0 plus 3, which gives us y equals 3. This confirms that our y-intercept is indeed 3, exactly where the line crosses the y-axis. Understanding these two components, the gradient m and the y-intercept c, gives us complete control over any straight line. The gradient determines the line's steepness and direction, while the y-intercept determines where it crosses the y-axis. Together, they uniquely define every possible straight line on the coordinate plane. Now that we understand what the equation y equals mx plus c represents, we need to learn how to actually find the values of m and c in different situations. There are 3 main scenarios you'll encounter, and mastering these will give you complete control over straight line equations. Method 1. When you have an equation that's not in y equals mx plus c form, you need to rearrange it. The key is to make y the subject of the equation. Once you do this, the coefficient of x becomes your gradient m, and the constant term becomes your y-intercept c. Method 2. When you know the slope and one point on the line, you use the point-slope form. The formula is y minus y1 equals m times x minus x1, where m is your known slope and x1, y1 is your known point. After expanding and simplifying, you'll get the equation in y equals mx plus c form. Method 3, when you have 2 points, you first calculate the slope using the formula m equals y2 minus y1 divided by x2 minus x1. Once you have the slope, you can use either point with the point-slope form to find the complete equation. Let's work through our first example. We have the equation 4x minus 2y equals 8, and we need to find the values of m and c by converting this to y equals mx plus c form. Step 1. We need to isolate the y term. Currently, we have minus 2y on the left side. To move the 4x to the right side, we subtract 4x from both sides of the equation. Step 2. Now we divide everything by minus 2 to make y the subject. When we divide minus 4x by minus 2, we get positive 2x. When we divide 8 by minus 2, we get minus 4. Step 3. Now we can identify our values. Comparing y equals 2x minus 4 with y equals mx plus c, we can see that m equals 2 and c equals minus 4. The coefficient of x gives us the gradient, and the constant term gives us the y-intercept. Example 2. We're given a slope of 3 and a point at coordinates 2, 7. We need to find the equation of the line in y equals mx plus c form. Step 1. We'll use the point-slope form. The formula is y minus y1 equals m times x minus x1. We substitute our known values, m equals 3, x1 equals 2, and y1 equals 7. Step 2, we expand the right side. 3 times x minus 2 equals 3x minus 6, so our equation becomes y minus 7 equals 3x minus 6. Step 3, finally we add 7 to both sides to isolate y. This gives us y equals 3x minus 6 plus 7, which simplifies to y equals 3x plus 1. Therefore, m equals 3 and c equals 1. Example 3 is our most challenging problem. We have 2 points, 1, 4, and 5, 12. We need to find the complete equation of the line passing through these points. Step 1. First, we calculate the slope using the formula m equals y2 minus y1 divided by x2 minus x1. We have x1 equals 1, y1 equals 4, x2 equals 5, and y2 equals 12. Step 2. We simplify the calculation. 12 minus 4 equals 8, and 5 minus 1 equals 4. Therefore, m equals 8 divided by 4, which equals 2. Step 3. Now we use the point-slope form with our calculated slope and either point. Using point 1, 4, we get y minus 4 equals 2 times x minus 1. Step 4. We expand and simplify to get our final answer. 2 times x minus 1 equals 2x minus 2. Adding 4 to both sides gives us y equals 2x minus 2 plus 4, which equals y equals 2x plus 2. These three methods give you complete control over straight-line equations. Whether you're rearranging an existing equation, working with a slope and point, or finding the equation from 2 points, you now have the tools to handle any linear equation problem with confidence. The equation y equals mx plus c is one of the most versatile and powerful tools in mathematics. It appears everywhere in our daily lives, from simple temperature conversions to complex artificial intelligence systems that make predictions about the future. Today, we'll explore 3 real-world applications that demonstrate the power and versatility of this fundamental equation. Each example will show you how the same mathematical principle applies across completely different fields. Our first example is temperature conversion from Celsius to Fahrenheit. This is a perfect example of a linear relationship that we encounter in everyday life, especially when traveling between countries that use different temperature scales. Notice how this formula fits perfectly into our y equals mx plus c pattern. F represents y, our output temperature in Fahrenheit. C represents x, our input temperature in Celsius. The slope m is 9/5, which tells us how much Fahrenheit increases for each degree Celsius. The y-intercept c is 32, representing the freezing point of water in Fahrenheit. Now let's apply this formula to convert 25 degrees Celsius to Fahrenheit. We substitute 25 for c in our equation. First, we multiply 9/5 by 25. 9 times 25 equals 225, so we have 225 divided by 5. 225 divided by 5 equals 45. So now we have 45 plus 32. Finally, 45 plus 32 equals 77 degrees Fahrenheit. This linear relationship allows us to convert any Celsius temperature to Fahrenheit using the same pattern. Our second example comes from business economics. A small manufacturing company wants to understand their total monthly costs. They have fixed costs that remain constant regardless of production, plus variable costs that increase with each product manufactured. In this equation, C represents the total cost, which is our y value. The number of products x is our input variable. The slope m equals 15, meaning each additional product costs $15 to manufacture. The y-intercept c equals 500, representing the fixed costs that must be paid even if no products are made. The company wants to know their total cost for manufacturing 200 products this month. We substitute 200 for x in our cost equation. We multiply $15 per product by 200 products, which gives us $3,000 in variable costs. Adding the $500 in fixed costs to the $3,000 in variable costs gives us a total monthly cost of $3,500. This linear model helps businesses predict costs and make informed decisions about production levels. Our final example demonstrates how artificial intelligence uses linear equations to make predictions. A machine learning algorithm has analyzed thousands of house sales and discovered a linear relationship between house size and price. The AI model found that house prices follow this linear pattern. P represents the predicted price, our y value. The house size x is our input variable. The slope of 120 means that each additional square foot adds $120 to the house value. The y-intercept of 50,000 represents the base value of the property, regardless of size. The AI system needs to predict the price of an 1,800 square foot house. We substitute 1,800 for x in our prediction equation. We multiply $120 per square foot by 1,800 square feet, giving us $216,000 for the size component. Adding the base value of $50,000 to the size value of $216,000, the AI predicts this house will sell for $266,000. This demonstrates how artificial intelligence uses the same linear equation principles we've been studying to make real-world predictions. These three examples demonstrate the incredible versatility of the linear equation y equals mx plus c. Whether we're converting temperatures, analyzing business costs, or building artificial intelligence systems, the same fundamental mathematical relationship appears again and again. Understanding this equation gives you a powerful tool for solving problems across many different fields. We've covered a lot of ground in this comprehensive exploration of linear transformations and straight-line equations. Now it's time to bring everything together and see how these concepts connect. First, we explored linear transformations, mathematical functions that preserve the fundamental operations of vector addition and scalar multiplication. These transformations form the backbone of many applications in computer graphics, data analysis, and artificial intelligence. We also mastered the equation of a straight line, y equals mx plus c, where m represents the slope and c represents the y-intercept. This fundamental equation helps us model and understand linear relationships in countless real-world scenarios. These concepts are deeply connected. Linear transformations can be visualized using coordinate systems with straight lines, and the equation y equals mx plus c represents one of the simplest forms of linear transformation. Now that we've reviewed the key concepts, what should you do next to master these topics? To truly master these concepts, I recommend 4 key steps. First, practice solving various linear transformation problems to build your intuition. Second, work with different forms of straight-line equations in various contexts. Third, apply these mathematical concepts to real-world scenarios. This will help you see their practical value. Finally, explore how these topics connect to other areas of mathematics, like calculus, statistics, and advanced algebra. Remember, mathematics is best learned through practice and exploration. Don't be afraid to make mistakes. They're an essential part of the learning process. If this video helped you understand linear transformations and straight-line equations, please give it a thumbs up. Subscribe to our channel for more comprehensive math tutorials, and don't forget to ring the notification bell. I'd love to hear from you in the comments below. What mathematical topics would you like to explore next? Whether it's calculus, statistics, or advanced algebra, your suggestions help shape our future content. Keep practicing, stay curious, and remember, every expert was once a beginner.